So good afternoon, welcome to the second lecture. And before we get started, it's nice to quickly recap what we did in the introductory class, right? So there, I pointed out that this course is really looking at addressing three questions. Okay? The first is about Brownian motion and diffusion, right? So we have seen most likely in earlier transport courses that when you have tiny particles suspended in a fluid, they undergo random walk type motion, which is called Brownian motion, right? And this microscopic motion, when you think of a collection of particles, gives rise to diffusion. Right? They're both from the same source, they're the same phenomenon. Okay? But you have two ways of thinking about them. At the individual particle level, you can track one particle when obviously its motion is stochastic and you need stochastic techniques to evolve it. Right? On the other hand, you can think of the collection of particles and the concentration field. And at that continuum level, you will get a diffusion equation or an advection diffusion equation, which is a fully deterministic PDE. Okay, so the question is, how are these two things related? And if you have one formulation, how can you find the equivalent, right, at the other scale, right, micro to macro? So this connection is fundamental and it's very important because typically, depending on the situation, you may have information at one of the scales and you would like to know what's happening at the other scale. So that's the first thing. So it turns out that to do the individual particle motion, you need a stochastic differential equation. And in the first lecture, we saw that this can be mathematically complex, and I showed you in an intuitive sort of way that if you try to define a SDE, you are led to a stochastic integral as a solution to that SDE if such a thing exists. But that integral is not uniquely defined, okay, because the integral depends on where in the integral you choose to sample this noise that you're trying to integrate. Okay, so we indicated there that there will be some mathematical complexity. So how to understand stochastic differential equations, how to solve them numerically on the computer or analytically, these are things that we will have to address. That's our second thing, right? So to learn a new mathematical technique called stochastic calculus. And finally, we are doing all this machinery because I want to apply it to turbulent transport. So that is the third thing, right? Where we ask, can I understand how turbulence creates mixing and mass transport by modeling the turbulent flow as a random field? Right? So if you do that, you replace some complicated solution of Navier-Stokes equations, you just take a field which is random. That means at every point I have some velocity, I can define it from a random number. Right? So it will be fluctuating and it should create mixing, one would think. And the question is, can you understand what turbulence is doing in terms of the properties of this random field that you specify? But immediately we saw that when we do this, something surprising happens. If you try to take the average behavior from such a random field, it seemed like there would be no mixing, which again indicates that things are not so simple. Okay. So these are the three questions that we are going to address, and today we'll start with the first one, okay, which is about how do we connect the individual Brownian movement of a particle to the field diffusion. Okay. And we'll do this in a historical way by looking at the early work on just this topic by Einstein and Langevin. Okay. So Einstein, so to go a little further back, Brownian motion comes of course from Brown, the botanist who did experiments on pollen grains, and really it was organelles from within the pollen grains that were super tiny, and he was tracking them in a liquid, and he saw that they were moving around erratically. So then this happened around 1827, and it took a long time for people to understand theoretically what's going on. And so in 1905, in a seminal paper, Einstein used statistical techniques to come up with basically a diffusion equation, right, which explained this Brownian motion and in terms of a PDE. Okay, so that is the first thing we will do. So this gives you the PDE approach. And the question is, just by thinking about a particle doing a random walk, how do we get a diffusion equation? Okay. So he sort of, in a way, you could say he bypassed that individual motion and went to the collector. So we'll see what he did. Right? It was of course a seminal derivation, so it is rough and intuitive, but all the important ideas are there. That's why we'll start there. And then 1 year later, Langevin did the same problem, but thinking about just the individual particle and explicitly modeled it with some kind of differential equation with some stochastic term to say that, okay, it's like a billiard ball, but which is being randomly tapped all the time. And then what can I understand from this? And he got the same results as Einstein, but in his words, in a way that was infinitely more simple. Right? So I leave you all to judge which one is simpler. Okay. But anyway, so the nice thing is these two historical works directly address the question that we are thinking about. okay, and they are also proximal in time, which shows that people were naturally thinking about these things in the two different ways that arise. I should also mention that 1 year after Einstein, Smoluchowski did something very similar to him, and much of the work in Brownian motion was done by Smoluchowski. Okay, so these are the seminal people. And in what I'm going to do now, including this, for most of the mathematical development in this course, including this kind of historical introduction, is there in Gardner's book. Okay, the details are in the course outline. It's a Springer book. Several editions are there. Anyone will have most of the material I'm doing. Okay, so with that, let's start with Einstein's treatment of Brownian motion. To keep things simple, we'll think of things only in 1D. Okay, and more or less, I'm doing as Gardner shows in his book what Einstein did, but here and there I'll maybe add something extra to help us along. Okay, so we'll do things in 1D, and you can think about the key ideas he introduced as being a couple of important things. Okay. So first, let's restrict ourselves to 1D motion. Okay, so now the important thing that Einstein recognized, okay, is that if you think about, so again, I want you to picture a Brownian particle. Those of you who are here in the first class can think back to the video I showed, right? So you have a particle and it's being bombarded by small molecules in the fluid, so it does this erratic motion, okay? Now, obviously, if you, in time, zoom in, right, and follow it very, very closely, it's not teleporting from here and going there, right? So it is, at some time, if you zoom in, it will look like it's moving smoothly, because after all, it is an object experiencing some force. Even if the force is fluctuating rapidly, if you slow down the movie, it will be some smooth motion. Okay. So the fact that it looks erratic is because you are observing it at a time scale which is much greater than whatever time scale you need to resolve those changes in the molecular fluctuations, right? So there's some time scale associated with the molecular bombarding that's presumably very, very small. So at the times of interest to you, it looks like it's making erratic steps, okay, or taking random walks, right? So recognizing that this is what we are interested in, right, at the larger time scale. So you can think about this particle executing a sequence of steps, and each step is random. That means it doesn't depend on the previous step. Okay, this is the key point. That is the meaning of doing a random walk. Okay. So in order to use this to make mathematical progress, right, Einstein said that we will divide time into small steps, right? So I'll put small in quotes. Small steps tau, okay? Right, and after each of these steps tau, time steps tau, the particle takes a step in space delta. Okay, so basically the idea is, I know some process is going on, and I want to look at it at time scales that are larger than the molecular fluctuation time scale. So that's what he calls tau, but that tau is still small compared to the overall time over which you are looking at the object. So let's say the object starts here and it randomly walks for a long time and then it reaches somewhere here, right? So if this takes some big time capital T, this tau is much smaller than that. Okay, so if you like, you can still think of it as dt if you are simulating some equation. But the microscale physics it's describing occurred even smaller time scales. Okay, so that's why this is some kind of intermediate time. Okay, small compared to the overall phenomena's evolution, but large compared to the molecular stuff that you have of course ignored and you are going to put into some random description. Okay, so that is tau, and the idea is, so that I'm standing here, after time tau I take a step, if you're doing it in 1D, right? So I take some step, again tau I take another step, then again tau I can take a bigger step, right? So you can keep doing this, and each step has nothing to do with what has happened before or where you are, because it's random. So that is the idea. Is this clear? What is tau and what is delta? So that is what he introduced. So this seems simple enough. So now when you do this, obviously you need to say something about this delta, right? How big is it and how often does it take those kinds of steps? So obviously it would seem like there should be less chance to take very big steps, right? Because if you observe the phenomena, it is not jumping suddenly, but it's also fluctuating. So given that you have frozen this tau to a fixed value, you can imagine that at different intervals, it would take steps of different sizes, right? And of course, forward and backward. So the way to describe this, the kind of information you need to give, is in terms of the probability of taking steps of size delta. Okay, so you have to introduce a probability distribution for the delta. Okay, a probability distribution function for delta, okay, which I am going to call phi of delta. Okay, and so what does this mean? So if you remember, I guess you have done in basic probability what is a PDF, right? So the PDF is defined such that if I am now looking for the actual probability, right, of taking a step delta, right? So let's say delta is just for the sake 1 millimeter, okay, or 1 micrometer. So the probability of a particular step size, right, is given by the PDF times d delta, right, where I'm integrating over all possible step sizes delta. So delta is a random variable, right, which can take different values. The question is what is the probability of taking any particular value? And because delta is going to be treated as a continuous random variable, that probability will be given by a PDF phi, which is a function of this delta. Okay. So it's a probability distribution or probability density function, because this phi times the d delta gives you the incremental probability. Okay, if you like, sorry, I should correct something here. This is of course not correct, right? This is the overall probability, which should be 1. Correct. So the thing I should be a little careful about. Yeah, it's best to write it differently. So the correct way to think about it is the probability of taking a step between delta and delta plus d delta, right? Because the probability of taking a particular step is not easy to define, right? It doesn't make sense. But taking a step in some interval, so delta and some small increment, right? That is given by d delta. Okay? And then later when we want to proceed in the derivation, we'll use this fact. Okay? So the idea is, you can imagine that I have a distribution of possible step sizes delta, which I will draw here. And f of phi. And now this is 0, okay? So there will be some probability of getting a step size, of course not exactly 0, because that's like choosing a point of measure 0 from the number line, which will have 0 probability. But what you can define is a probability of taking a step size in some interval. So let's say I am asking what is the probability of taking a step close to 0, okay? Then that will be given by phi of 0 into that interval. Okay. So that will have a finite probability, which I can define. So now the question is, what kind of probability can you imagine? So if you say that the particle is going to take forward steps and backward steps as likely, okay, then this phi should be something symmetric. Also, you might guess that it has a higher probability to kind of take small steps, right, than to take very, very big jumps, just from maybe a physical observation of things. So you would expect the probability to decrease, okay, as the step size becomes big. Otherwise, you'll see the particle undergoing these huge jumps, which is not physical. Right? Certainly, you know, as delta goes to infinity, this phi should decay very rapidly. So what we can say is that this phi should tend to 0 as delta goes to infinity. And then there are interesting questions about, is the phi symmetric, right, if it's equal, forward and backward steps are same. But this need not be the case, right? You could imagine that there is some bias for some reason in the walk, right? And then forward steps are somewhat more likely than backward steps, right? In that case, you would have some other kind of thing like this maybe. Okay, so that's also possible. Now, of course, in the particular Brownian motion that we are considering, it should be symmetric, because there's no reason for there to be a bias in any particular direction. But for generality, let's not commit ourselves to that for now, but just keep it in mind. Okay, so this was the initial physical picture of what's happening. And now what is the goal? Okay. So what we want to do in the end is to say, okay, if I have a particle at some point and it's undergoing these steps delta with some given probability distribution, what I want to know is what is the chance of finding this particle at some later distance x. Okay. Or if I think about a collection of particles, and I say I start all the particles from the origin, I want to know how this concentration of particles is spreading out in time. So my goal is to find the probability distribution function of the position x. Which is p of x comma t. So now time comes in, okay, for the first time. So this what I defined, phi of delta is not a function of time, right, because it's a property of the particle and the path it is in and how it is taking random steps. That doesn't depend on time. But how the particle is evolving, this is really what's evolving in time, right, where it is moving. So finding the probability distribution of the particle, right, this would be equivalent, as we discussed in the last class, to finding the concentration, right, if the system is dilute. Because then if you have a collection of particles and the system is very dilute, you're going to assume that each of them are moving around as if they don't see anything else. Okay. So then the probability distribution of that particle's position is the same as the concentration or the number of particles per unit volume, right, because you can define the probability at some point x as the number of particles you find there, right, normalized in some way, divided by the total number of particles. Okay, so this is the same as trying to find some equation for some kind of normalized concentration of the particles. But since we are working in probabilities, we'll think about this for now, that I just have one particle, all right, and it is moving around, and I want to find the probability distribution of that particle. But if I then take n particles, n into small p gives me the concentration. Okay, so now what do we do? So really what you're doing here is, as in all mass transfer, it's a mass transfer problem. Right? And so the first step in any mass transfer problem is what? So we obviously want to write down some equation, but what principle will we use? Yeah, you do a mass balance, right? So in general now, when you're in the basics of any physical science is to start with the conservation laws, right? And if you're doing a mass transfer problem, it will be the mass balance. And then you see if there's a velocity and if there is some other properties like diffusivity, you have to provide some relations for them. So here also we will start with something equivalent, but especially if you're thinking about just one particle, we want, I mean, there's only one particle. It's not that the particle is disappearing, but what we have to do is conserve the probability. Okay, so we are going to do a probability balance, conservation of probability, right? Because the particle has to be somewhere. If it is here and it moves there, it has to increase the probability of finding it at that new place. But if you think about it as doing a kind of mass balance, the idea will become intuitive. But we'll arrive at that at a slightly different way from what you have seen before. Okay, so what, and this is Einstein's derivation. So again, some steps will not make total sense, but the important thing is to get the main ideas, and then later in the course, we will see how we can put this on a rigorous footing. Okay, so what he started with by saying that, okay, I want to find this P. So I'll make some kind of probability conservation statement, which is that the probability of finding P at some x, so, and at the next time, t plus tau, okay, is equal to saying that, okay, let me look at the probability at t, right? So I have some, so again, you can think of it either as probability or if you like, as a distribution, concentration distribution, right? So it's helpful to see both ways. But if I say, okay, let's say that there was some probability of finding the particle at x at time t, and then it underwent a step delta, it would take me to a new position, and I should increment the probability at the new position x plus delta. So if I do it backwards, it will be like saying that I will have a certain, also it helps instead of probability if you think about number frequency. Okay, so what is, how many particles will I have here as a fraction of the total, right? That is like the probability. Right? So that depends on how many particles were there at x minus delta that then took a step of size delta. Okay, so it's a probability of having particles at this position at time t who took a step of size delta. So I will then have to put and then I need to integrate over all the possible steps, right? So this step could be some small delta, some big delta, and I want to account for all of it. So let's say there is this step, then I need to see how many particles were there and put them in this box, right? But I could have also come from further away and taken a bigger step, right? So that just means I need to keep varying this delta and integrate over all deltas. So then I will put this minus infinity to plus infinity. And as I said, it makes sense if you think about P as the number fraction of particles, right? So the number fraction of particles at this position at the future time is the number of particles that were there at x minus delta, which took this step delta. Yeah.
We are the ones who are setting tau.
Yes.
So why don't we take t minus tau on the RHS instead of taking t plus tau on the LHS, because it doesn't survive.
Yeah, you can do that. It's fine. You try it at home. It should not change anything. Right? Anyway, time has no, the point is you are taking the difference, right? So it's useful to try it in different ways. Okay, fine. Yes.
What about the particles leaving this position? These are all the particles that are entering that. Shouldn't there be one more term for all particles, all the probability leaving? So P of x comma t times phi of delta integrated.
So, yes, I mean, on the surface it sounds correct, but you would end up you will be double counting, okay, because you have to think about the way we have set it up. So, okay, so maybe if you think about it this way, all the particles everywhere are taking some step of delta, okay, and what I am saying is, what is the number fraction here? I am going to all those step sizes, right, and changing the position accordingly. I am not fixing the position. What you are thinking of is, if I say this particular position, now I have to count who left this position, but this position is not constant. You see, for every delta I am changing this. So I am not fixing the bin, right? You are thinking of, suppose I am standing in this, only in this box. Then to find how many guys are in the box X, I should add guys who came in and remove guys who came out. But that's because you are sitting in the same box. I am not sitting in the same box. I am changing the box. You see? That's why I said it's different from the classic mass conservation where you fix an Eulerian frame and do input minus output. This is not the same as that.
But on your left hand side, you have already the function of x. X is staying at this position, and then you're saying what is the.
Yeah, but the way I'm doing it is not by doing input minus output, right? That is what I'm trying to say. Okay, so maybe if we can talk about it more later. All right, so is this okay? So now I'm integrating over all step sizes and accounting for all the stuff that would have taken just those steps from different positions that brought them here, right? So now, yes, okay, so that's fine, but it at present doesn't seem how I can get in. So what do I want to do is get an evolution equation for P, because I want to know how P is evolving in time, all right? And this is fine, it's just a statement of some kind of probability conservation. The question is, how do I get a differential equation or some kind of evolution equation for P? So any ideas what I should try to do? What should I do next to try to get some kind of differential equation for P? And remember, what we're trying to do now is, you know the answer in the end, right? We are going to a diffusion equation. So somehow I have to introduce derivatives of time and space. So what do you think Einstein did? Sorry? Okay. So what should I do? No, but you're saying apply a derivative. No, but that will just give me the double derivative. No, how will it introduce time and so on? Very good, right? So you will do a Taylor series, right? Because that's how it has been set up, right? In fact, the whole idea, remember, is he's made it an important point to say tau is small, right? Relative to the overall evolution of the variable t. So if you're going to track the process in time of how this thing is evolving, that's over some longer time scales that you're interested in the overall transport of particles. Compared to those long time scales, this tau is supposed to be small. Okay? Yes?
Can we think of it like in this equation where for the case of delta 0, we are only taking the counting the particles that are at x which will not move. Because then delta is
Correct, that's what will happen. Yes, yes.
getting accounted. We are not taking into account all the particles that did move. Like we are only counting the particles at x which did not move.
Yes, so yes, correct. That's if when I say delta is 0. But so there will be some particles at x that did move, but those are not being counted. Correct. Because they won't be there at x, right? If they move. So he was saying output, right? So it's not formulated like that, but in the end what you're doing is saying, I know the step everyone took, and I know that only those guys who took a step delta and were at those appropriate positions will end up here. This is the statement. Right? But now if you try to think about it in terms of input minus output, then you have to do some, you have to think of it. Okay, fine. So let's get back to the Taylor series thing. So like I said, see, this is not the most clean. It requires a little bit of thinking, right? But that's why it's important, right, as a first study. Okay, so let's get back to this. So now what he did is to say, let me do a Taylor series because I want to introduce these derivatives. So you do a Taylor series in time on the P here, and you do a Taylor series in space here. Okay. Right, so what will this be? Of course, at the time x comma t, I am not writing that. And then this chap. So I'm bringing everything into x and t, right? That's the nice thing. And then I have to account for this. So what will be the next term be? Plus or minus? Minus, right? Because there's a minus there. So it's the distance from x, which is minus delta, into dou p dou x. And now should I, so here I stopped. No? So should I stop here or should I take another term or what should I do? Oh, sorry, I forgot about the phi. I mean, I'm not doing that now, I'll substitute it later. The point is, yeah, so should I add another higher Taylor series term? Yeah, what were you saying? So think about what happens if I put it back here, right? So this term will be dp dx delta phi. Yeah.
For small deltas, the Taylor series goes first order.
Yeah, we are only doing small. So the question is, should I stop at the first order? Or is there some reason for me to want to go to second order? Here I should definitely stop. I mean, because I'll get the ordinary differential equation for p, dp dt is equal to something, right? And it would be the dominant term. But here should I say, okay, enough, or is there some reason, some circumstance at which I will have to take the second derivative? Or if you can't see it right now, then let's proceed and maybe later it will become clear, right? So I'm going to go now and then we'll see why we should go later. So what should it be? Delta square by 2 factorial, which is 2, and the second derivative. And then I'm going to neglect the higher terms, right? Higher order terms that will be small compared to these terms. All right, so now what should I do is I'll put this stuff back in here. And the nice thing is you will see that these things now no longer have delta in them, right? The delta dependency is made explicit and I'm only integrating with respect to delta. So I can pull out the partial derivatives of p and I'll be left with integrals involving delta and delta square. Okay. And if you look at this first term, it will just become, the p will come out, I'll have integral over phi of delta d delta, correct? And what should that be? What is integral phi from minus infinity to plus infinity, right? That was the goof up I made there. So it will be 1, right? Because you're saying what is the probability of taking some step delta where I'm summing up all possible deltas. So of course, it's like saying what is the probability of taking some step of any size, which should be 1 by definition. Right? So when I introduce phi, part of it is that phi is normalized such that its integral from minus infinity to plus infinity is 1. Okay, so this term will just give me p and that will cancel out with this p. Okay, so let's see how that happens. Okay, this is going to be a bit Okay, I'll need your help. So if I substitute, you all have written it down? Yeah, somewhat, okay. So I substitute back, I have dou P dou T, right? On the left hand side we just had P plus, and then there was tau in front of it, right? P plus tau dou P dou T, correct? Where now P means at x comma t. And then this was equal to, remember I said I have integral so I'm going to put that expansion, right? So this phi delta d delta will come with P will come outside. I will then have minus, right? Yes, and then plus half so I just substituted it and pulled out the p's which don't depend on delta. Is that okay, or did I forget something? It's fine. Okay, so now the fun begins. So I can write this basically as p into 1, right? Because this integral is the probability of taking any step of some size. So this is just p into 1, and this p will cancel off. So now I have a nice evolution equation for dp dt with that factor tau. And then I have now two more terms. Okay, so you can see now this is a function of x and t, this is a function of x and t, and these things in front of them are not functions of x and t, they are some constant coefficients that depend only on this probability distribution I specify for the step, on the properties of the step. Okay, so you can already start seeing that if you look a little ahead, this is some constant into the second derivative, so this will give me diffusion. Right? This is like a diffusion coefficient. Right? If you interpret P as the concentration, and this is then what? Advection, right? It's a velocity. Because the velocity times dp dx, no? That is the advection term with the correct sign. So I would have to move it to the other side. Right? So if you think of it as a concentration, I'll have dc dt plus u dc dx is equal to diffusion coefficient d square c dx square. So it has exactly that form. Okay. Now what? So that will make it interesting, right? This is basically advection, which will exist when only when you have a mean flow. Right? Otherwise, it doesn't make sense. So if we think of our situation where it's a still fluid and it's just moving up and down, then this should be 0. But otherwise, I mean, it will not drift in some direction. Why should it do it? It should be symmetric. So what will guarantee this being 0? What property of this phi, which comes out naturally from the physics, is the symmetry, right, which we had indicated. Right. So this advection, so if I want to say this whole thing can be u, right, and this u will be 0 if the probability of taking a forward and backward step is the same. Right? So then there will be no net advective movement. Okay, so now of course this u doesn't have to come from the fluid moving, right? It could just be that I have a particle that is undergoing some random motion, but I'm also imposing something, let's say that it's a particle in a fluid, but it's a steel ball and I put a weak magnetic field, so it starts to be pulled in one direction. Right? Then this would account for that. And so the u would be the drift that is coming because the steps are not symmetric, and that u would have to be related to the electric field force that I've applied or something. So it doesn't have to be a velocity in the sense that the fluid is moving. It is just some physical force that's introducing a bias and making the particle drift. And there can be many physical sources. Okay, but so in terms of this balance of probability equation, right, which we will call the Fokker-Planck equation, this is the advection or drift term, right, which can have different physical origin. And it has to do with whether there is any mean drift or not. And if it is not there, you just have pure Brownian motion, pure diffusion, then those step sizes will be symmetric. So if you had started with this, you would have seen that this term would fall out, which means it is not the leading order term and you need to take the higher order. Right? So automatically when Einstein was thinking about this problem, he just said it's going to be symmetric because he's thinking about normal Brownian motion. So this would anyway become 0. So he had no choice but to go to this higher order. And now even if you think this is there, you of course know this is not going to give you the diffuser motion, and therefore I need to go to the higher order to be able to see the diffusion. Okay, again, see, these are not rigorous arguments, right? But the point is, intuitively, if you think about what you want to get, you can see that I need to take the second moment. Okay, these are also moments, right? So the other nice thing is that if phi is the probability distribution of the step, the first moment is the drift, right? And the second moment of this PDF, it gives you the diffusion. Okay, so then finally now I get an equation like this, right? So let me keep the u just for, so Einstein didn't have the u because he was not considering things with drift, but let's just keep it for completeness. Right, which is such that the u is the first moment and by tau. Okay. Factor by 2 I'll take in. Okay, so I'll just keep the question. We'll come to general, we'll sit back and muse about it in just 2 minutes, but let's just see if mechanically people are happy. Okay, so that at least the derivation steps are fine, and did you get this? Yes. Okay, so then some other checks just to make sure we didn't do anything funny. So we have got a velocity here. Does it have the right drift velocity? Does it have the right units, right? So this is going to be a step. This is the mean step. Correct. Phi has no, phi has units of 1 by d delta, so that will go off. So the only unit is that of delta, which is the length, and you have a time, right? So it's length by time, and similarly this is length square by time. Okay, so it has the correct units of diffusivity and advection. And now you can see that in terms of that phi that I had plotted here, right? And let's assume something like this, which has some drift. Then the mean step, which is the first moment, right, contributes to the drift, right? So if the mean step is 0, then it will, it not means it will not move, right? It means there will be no net drift because you're still stochastically fluctuating. But there is no mean step. Mean step is 0 because I go forward and backward equally, right? So the mean of the steps of my random walk steps give me the, if it's non-zero, it'll give me a non-zero drift. And the diffusion, which has to do with the mean squared displacement, right, as we know. So if I do blah, 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 if I take one particle and I move it around, it will end up somewhere there. I take another particle, it will end up somewhere else. And if I do this, they will all be symmetric spread around, so that their mean position will still be 0. Right? That is the meaning of this thing, that no drift. But if I look at the root mean square displacement, so this is plus some distance, this is minus some distance. If I square those distances, then I'll get a non-zero number. And that tells me how much this ball is spreading. Right? That has to, of course, do with the diffusion. Right? And so the second moment of this distribution, now if it was centered about 0, with no drift, the second moment is just the variance, right? So the variance of this thing contributes to how much it is spreading. Okay, so you can see the nice thing about this again is it's showing you the connection between the field level properties, right? The drift velocity and the diffusion, and how it connects to the microscopic behavior that you would have to either specify based on some microscopic physics or based on your observation. Okay, so now you can imagine that if you're doing an experiment and you're observing a particle and you can watch it, you can make a bunch of movies and you can define some tau and discretize those movies and get statistics of the steps, then you have phi. So this is a completely implementable thing. It's not some pure thought experiment, right? So I can actually watch a particle moving, right? I can choose some tau and for which is large enough so that those steps are becoming random, right? And then you can get the statistics of phi of those steps, the distribution, and then immediately you will get the diffusion and the drift. And you can solve now the field equation. You don't have to try to develop a model for the microscopic motion. So without trying to do any fancy math, just from the statistics of the steps, right, I can write down the diffusion equation or advection diffusion equation. So this shows you the connection between what's happening at the micro scale and what you're seeing if you write down a field equation and vice versa. Right? Suppose if somebody came to you and said, for some reason I have this advection diffusion equation, but I want to know what kind of particle it could correspond to, right? So your answer should be this kind of behavior of the concentration field of the particle will be given for any particle that has these properties. And so immediately now you see that it's not a one-to-one relationship, this micro-macro, right? Because many microscopic particles doing very different kind of stepping, as long as their mean and the variance is the same, they'll all give you the same advection diffusion equation, right? So it's non-unique, this mapping. Okay, because many different phis, right? I can think of many different phis which just have these two moments, right? The full distribution to define if it's not Gaussian, you need all the moments, infinite moments. Right? So you're just using the lowest order moments, only the lowest order moments are needed in the field equation, which tells you that this is somehow already averaged out, right? You have lost a lot of microscale physics because those are not relevant at these at the large scales where you're just looking at the field. And if you ask, where did I make this assumption that I'm looking at the large scales, that's what you did in the Taylor series. Because otherwise you cannot say, if you're looking at things at the scale of delta, you cannot Taylor series. You did the Taylor series because you're saying tau is small, delta is small compared to what I'm interested in. So you already went from small scales to large scales. In that sense, you did some kind of averaging and you lost some information. Okay, so these are things that we will see again more rigorously, that it is not possible to have a unique mapping, right? Or in other words, many different microscale particles can show you the same advection diffusion equation. Okay, so yes, maybe now I can take your question.
When you said that u is equal to 0, it implies that the particle can move forward or backward with the same probability. When we have an imposed velocity, does it mean that imposition of the velocity introduces bias, or is that argument not applicable?
If you, so yeah, can you say it again, please? If you impose a velocity, in what sense? That I am making, it's sitting in a fluid and the fluid is flowing?
Yes.
Or I am, let's say, I have a particle and I somehow apply a force and pull it, or either case?
When you're moving the fluid and then the particle is moving.
Okay. Yeah, so that's perfectly fine. So let's say I have, so imagine I have a particle in a still fluid, right? I will have this equation. And now if I say, no, this entire fluid is moving with a velocity u, then I will get this equation. And this will be that velocity.
Okay, so
and automatically that will happen here, right? Because the microscale Brownian fluctuations, thermal fluctuations don't care about your macroscopic velocity. There's a scale separation, right? So if I look at, that's the idea of local equilibrium, which we use all the time in applying thermodynamics to transport processes, right? So you think about all your previous courses on transport phenomena. We use relationships of viscosity's dependence on temperature. We use ideal gas law if you're dealing with flow of gases. These are equilibrium thermodynamic relations. But your fluid is not in equilibrium. That's why you are studying its flow. Okay? But the idea is that locally in that small place, things are relaxing fast and you have local equilibrium. That's why you can use these relations. And that's coming basically because you're saying the thermal fluctuations are at equilibrium, even though the large scale flow is not at equilibrium. And so that same idea will tell you that I have some phi when the fluid is completely static, right? That has some distribution which will give me d. U will be 0. Now there is some large scale motion. That large scale motion I'm saying is not going to affect the noisy part which gives me d. It's only going to just add on. So the large scale stuff is just adding on to the small scale thermal physics which is at equilibrium.
But then we are saying that when we impose a velocity, that changes the probability.
It just adds a constant to phi. It just shifts phi. It's not changing the fluctuations, you see. So it's like, imagine you had a Gaussian distribution for phi. with zero mean. Now the mean will be the whatever velocity you impose. So it's just added a drift. It's not changed in some fundamental way the small scale fluctuations. But that's not the only way you can get drift. That's what I was trying to say. You can also create some bias. So this happens if you have what are called active Brownian particles which arise in biology, like a bacteria. Okay. So bacteria also, they swim for some time, then their flagella unfurls, they change their direction randomly, they swim some other. So if you watch them, it will do some stuff like this. Okay. So it looks like it's Brownian, but it's also swimming by itself. And then if you have a nutrient gradient, it can swim in some mean direction even though it's doing. Right. So there the drift is coming because of something happening at the level of the particle, how it is sensing its environment and so on. So in biological problems, very often the drift will have to do with something at the small scale, not something I'm imposing from top. Okay. But this thing is general, right? So it accounts for all variance. Okay, so any questions on the mechanics of what we did, just in terms of steps? Okay, if not, then I want you to sit back and again look at what we did and see if anything is troubling you. So think, for example, of the Taylor series move that we did. Okay, so now we recognize that it's a nice derivation, right? Seminal because nobody had done this before, introducing many, many new ideas, right? Which was Einstein's genius. But now 100 years later, we have developed more rigorous tools that in the end give us the same results, but by generalizing certain things and removing certain problematic aspects. So one of these aspects which might occur to you is the fact that we did a Taylor expansion in delta, right? Assuming delta is small. But remember, I have defined probability distribution for all deltas, correct? And I have not said anything, I'm not saying the phi has to be absolutely zero if delta is, there's no such statement. So you can imagine that there is some chance that I will get some large delta which is going to violate my Taylor series, right? Because the idea of Taylor series is, in principle, I should make delta tending to zero. But that doesn't immediately jive with the fact that I have defined a probability distribution for any delta. It's certainly not tending to zero. Okay, so strictly speaking, it's not that the delta is some control volume that I'm shrinking. That's what we do in continuum mechanics, right? We take a control volume of some size, then you shrink it. So that operation, I can shrink it as much as I want, right? In the continuum world, it is indivisible. But I cannot do that here, right? Because it has some distribution of sizes. There is a mean variance on the size, right? The variance is not zero. So that's a little funny. Also the fact that you have tau, right? You defined a certain tau. And the question is, how do you know that you can always find this tau? So another way to think about this is, we have just done this derivation for some particle undergoing some kind of Brownian motion. Does this mean that all particles which are in a heat bath, which are being bombarded by fluctuating molecules will always give me advection diffusion equation? Right, so if this derivation is correct, there are no loopholes, then I will always, the particle cannot do anything else, it just has to diffuse it. No matter what the physical, because I've said nothing about the physics, right? I've been kept saying put the particle in the bath, but nowhere have I put that, right? I've just talked about steps. So you can think of cars in traffic, which have some mean drift, but you're changing lanes or something, and I can do the same kind of description, right? Nothing stops me. Because all I have said is I have some particle which has some distribution of movements. So does this mean that no matter what the physical situation, I will always get only diffusive motion from fluctuations? Or is there some thing we have assumed here which could be broken, and in which case I don't have to get diffusive motion? So to make it concrete, how many of you all were here in the last class? Right, so a decent number. So there you remember I showed you this example of those tracer particle motion in bacterial turbulence. Right? Sorry. Yeah, super diffusion, right? So, so maybe this we should do first. Okay, let's put a pause on that. We'll come back to this question. Do all particles subjected to fluctuations necessarily have to show only diffusive behavior? Because from this it seems like this is always applicable. Okay. So to make it more concrete, what do I mean by diffusive behavior? Let's just do a couple of steps that will make it more concrete, and then we can ask ourselves, is something else possible? Yes.
When you asked that we assume that delta to be small, but we made phi for all delta. So the question that arises is how would a large delta arise physically? It would be by multiple bombardments back to back in the relatively similar direction, which would
No, so large means what, right? The point is you cannot shrink delta as to any distance you like. That is what I'm trying to say. Large doesn't have to be large in some weird sense. It will have some distribution. That this distribution is not tending to zero, that's all. You don't need to have some weird successive bombardments and all.
But if we do not have bombardments in the similar,
No, you will still have some fluctuations, right? The point is, are those deltas arbitrarily small? They are not arbitrarily small. So then how can you do the Taylor series? That's all. It's not something in your control, right? That you can, so when I say delta tending to zero, strictly speaking, I should make the phi such that it squeezes the delta, but I'm not doing that. Right? The phi is whatever it is only, and then I'm taking delta to zero. This is the part. Anyway, so let's set that aside and see what is the consequence of this. So mean square displacement okay, so when you have a Brownian particle and you're looking at it under a microscope or something, the simplest thing to measure is what is the mean square displacement of the particle. That means I will maybe do many experiments with many particles starting at the origin, and then I'll do an ensemble average of the position x square, assuming that I start at the origin. And this in turn, by definition, is x square. This is a function of time. Okay. And so therefore I need to know P. So P will come from this equation, right? And now I am going to have u0 for Brownian motion. Right, so if the u is 0, then I just have this nice diffusion equation. And if I start with so if I'm starting at the origin, it means I should start with a Dirac delta initial condition, right? So you know the Dirac delta function, right? The impulse, second impulse response, and then you see how it spreads out. So all the particles are concentrated at 0. So that situation would be like starting from this Dirac delta initial condition at 0, and then you see how it spreads, right? So you would know, I guess, from your earlier courses that this problem has a solution which is just a Gaussian, right, that spreads out. That's like the fundamental solution of the diffusion equation. No, so it's so I'm saying that at the origin delta it's a Dirac delta function. Otherwise, it is 0. So delta is a function of x, and whatever x value you put, that's where the Dirac delta is located.
So then the arguments should be x minus 0. It's only when x is equal to 0. The interior of the Dirac delta is 0.
Okay, I was defining it as okay, yeah, that's fine. Fair enough. Or it's just x. Correct, thanks. Okay, so if you're defining it that delta of 0 is where you have the spike, and for all other x it is 0, then this is the thing. And then it will slowly spread out. Right, as you go forward in time. Okay, so that solution Okay, so the solution is a Gaussian whose amplitude decreases in time, right, to conserve mass as the variance spreads out, right. So this is the variance in the bottom. The variance is growing linearly in time, and because the particles are spreading out, of course, the amplitude at the center has to fall, right, to conserve mass, and that's what happens. The amplitude falls as 1 by root t, and the variance increases as t. And so if you plug this into that and then do the integral, right, what you will get is the mean square displacement, right, averaged over many particles. Yeah, okay, so let me take mean square displacement. And the root mean square displacement will be square root of 2 dt. Okay, so this is just a standard fundamental solution to this diffusion equation. The point is just to say that once you do this, you can show that the root mean square displacement of the particle grows linearly in time. Or if you look at the root mean square displacement, which has units of space, right? So if you imagine that you put many particles and they spread out like a ball, the rough width of that ball, which is the root mean square displacement, will grow like root t. Okay. So whenever you see that there is a ball and its radius is spreading like the square root in time, you should think diffusion. This is the fundamental feature of diffusive motion. Okay. And this is true again and again. So let's say you have in your transport phenomena course, you have done this problem where you have a fluid and then you bring a heated wall in contact with it. Right? And then you'll see that the temperature starts to invade and you have a boundary layer which grows. That boundary layer will grow as root t. Or if you suddenly you expose it to a slab of some concentration and material is diffusing, you will have a boundary layer which will grow again as root t. Right? So this root t thing will keep coming up, and it all has to do, of course, because the stuff is diffusing and the typical distance that diffusion allows you to cover grows like root t in time. Can you tell me of a situation where if you have a ball of particles and the radius is spreading linearly in time, what would that correspond to? To contrast diffusion to some other physical phenomenon, which is not diffusive. Anyone? So I'm saying take a bunch of particles and then you don't know what's happening to them, right? You can just observe particles. So you're seeing particles here and you see that they are growing. The question is what could cause them to spread apart? Now we have suddenly learned about Brownian motion and we are thinking, okay, that they are, but there could be other reasons for them to move apart, right? Too complicated here. Just think of particles, they could be cars, they could be billiard balls, they could be anything. You just know that there are some objects and they are spreading apart. They could be people. So if you see them going like root t, you will say, okay, whatever they are doing is a diffusive type motion. Is there any other kind of obvious motion where they would not spread like root t, they would spread differently? Something very simple. So suppose I make all of you stand in the middle of this room. Okay, you all have played four corners. You know this game, four corners. You stand in the middle of the room, you play music, you stop the music, you have to run to the four corners and then I call one counter and send you home. Right, so suppose you're all here and then after time t equal to 0, you all just run at some speed in all directions. How will that spread? You're all running with some velocity v, so how will the distance between two extremes increase in time? Linearly in time, right? So this is ballistic motion. So if you take particles or billiard balls, right, you have you set the rack and then you break, right, the ball spread out. That spread is linear in time. Okay, because you have some definite finite velocity and x is going like v into t, or delta x goes like v into delta t, you will spread linearly. So if you don't know what is the physics, you're just looking at, that's what this course is about, right? You're looking at transport and you're trying to understand how can I model it without knowing all the details and what are the different kinds of modeling and so on. So the simplest thing, of course, is ballistic motion. This is what Newton did. right? So he just said there are balls, if they have some velocity v, they will keep moving, etc. And then you just use basic kinematics. His position is velocity into time, correct? So if you have x square growing like t square, right? Or root mean square growing like t, that means x growing like t, then you know it is ballistic. So whatever is going on, that stuff for some reason has velocity, fixed velocity, and it is increasing in time. Right? So it could be because the particles are active like people and that there's some panic situation and they're running. Right? Or it could be because of some physics, or it could be an explosion or whatever. Right? But the point is that we would call ballistic motion. Maybe there's a bunch of swimmers and all the swimmers are moving, whatever. But this is now to contrast it with that. Right? So when you see something not growing like t, but actually growing slower at long times but faster at early times. Right? Because remember, if t is a straight line, x square goes faster and then it will be slow. Okay, so long time at large distances, diffusion is weaker than advection, but at early times it is explosive. You separate much faster because of these random steps. Anyway, so this grows like t square. So that is a classic signature of diffusion. So coming back to the example, it would be like if you all started in the middle of the room and then at a party, people start mingling and having conversation. Over time, the group will spread, right? And if they are just randomly walking around and doing stuff, that would be like diffusion. Anyway, so I just wanted to make this point that the signature of diffusive transport is this root t. So now coming back to my question, right? Can you think of situations where, so the point is, ballistic, yes, it will be t, but if you have a particle that is undergoing some fluctuation driven motion, right? It's in a thermal bath, it's being bombarded, and that's why it is doing Brownian motion. So any such particle, will it always give you this diffusive behavior? You could also think of a particle in turbulence, like the bacterial, so now you think of the bacterial turbulence video, right? So there I showed you that it's not always diffusive. When the flow is weakly turbulent, it goes like root t, or x square goes like t. But when the flow becomes strongly turbulent, it starts growing like something greater than t, right? T to the 4/3. But there also the motion, if you remember the picture, was chaotic and fluctuating. So now forget about the physics. If you think about the derivation, where in this derivation have I made some hard restriction that is forcing me to get diffusion? That is the question. So you should ask yourself, what in this equation would prevent me from getting root t, right? So if I get a higher order term, it's not really going to stop that. I will still have this as the, it will give me some asymmetries and all that, but so I should not be able to even write this. I mean, in fact, if you think about it, there is no simple PDE that will give you behavior like t to the 4/3. Because the first, so this will give you ballistic, that's fine. But how do you get some weird fractional power? It will not come. In fact, mathematically, it comes from some fractional kind of PDEs, which are some weird mathematical quantities. But from what we have done, it will not come from higher terms. So one assumption we have made immediately is that this moment exists. It's not infinite. So there is a finite thing. Okay, that's still okay. Actually, so I take back what I said. What he said was, what about the higher moments, right? So that's a fair question. If the PDF phi is well behaved, so that the higher moments are smaller, then keeping them will not do anything. But what could happen is I could have a weird distribution, right, which has fat tails. So it could still be decreasing, but is it decreasing fast enough, right? So remember, this d is coming from the second moment, right, delta square. If I had a higher moment like delta 4 to keep things symmetric, right, fourth moment, it would be delta 4 into phi, and that could blow off to infinity. So even if the phi decreases, right, because the point is for delta 4 into phi to be finite, the phi has to decrease with delta faster than delta to the minus 4, otherwise it will blow up. So even if you have a phi that's decaying like delta to the minus 3, it will give you an infinite answer as you integrate to infinity. So this means that there could be a system where I take large jumps, where very large steps are still rare in the sense that phi is decreasing with step size, but they're not as rare as I would think, right? There are these extreme jumps. And that would give me an moments that cannot be defined. That means they're blowing off to infinity. And this is what happens in that bacterial turbulence, that they take these large jumps with higher probability than a diffusive system. And in such cases, I cannot do this operation because if you go back to the derivative, right, even though delta 4 is small, this moment is infinity. Okay, so I obviously cannot drop it then. So then the derivation will break down. So I need this phi to be well behaved in the sense that all its higher moments are finite. They don't have to be 0, but they should not blow up. But they can blow up if you have these rare events, if you like, high probability rare events. And this can happen if you have some weird physics where most of the time you're doing Brownian motion, but then suddenly you get a big kick and you take a big step. And that's what happens in that bacterial simulation video, where the turbulent flow has some funny behavior where it creates these jets and then it transports the tracer large distances, rarely, but with enough frequency to break the diffusive behavior. And then you will start seeing that this t will not grow like half, but faster than half. Okay, like what we saw in the last class, right? 2 by root 3. The flip side of this, okay, is, so what I was trying to do now is just point out some caveats, right? So you should not think from this derivation that because it seems it has the appearance of generality that any fluctuating transport problem particles appearing to do random things, it must be diffusion. This is not true. Right? And the reason we can see it from this derivation, how as a cautionary thing, is one, I'm assuming that there are no high chances of these big steps, right? There's no physics that will give me that. Normal Brownian motion doesn't do that, but there can be situations where you have these big jumps. They are called Levy flights. Okay? And after Levy, the probabilist. And then you will get growth in time that is stronger than t, like t to the 4 by 3. That's called superdiffusion. Now there can be also systems where your particle gets trapped. So you think about diffusing, but in some porous network, like diffusion of a particle inside a filter, which is very relevant, right, for chemical engineering. So now you imagine you're sitting here, I am diffusing, but my domain is not free. There are obstacles. And I can get trapped in some obstacle, and even though I'm diffusing, I'm unable to move because I'm trapped. Right? In biological systems, polymer networks, this is an ubiquitous thing. Right? You have some drug molecule and it can go and get stuck in some polymer chains, and then it will eventually escape, but it has to break the cage, this kind of stuff. So such systems can show subdiffusion, where instead of growing like t, it will grow as a lower power, something less than t to the 1. Okay? Because they stay trapped for a long time, then they move. So that slows them down. And that will break this derivation, because what you will see is when I assume tau, I assume that there is some typical time I can take. But if the system gets trapped, the particles can wait there for very long times, much larger than this tau. That means that tau is not going to allow me to get the correct statistics, right? Because I would be using tau to define the phi, but the problem is there are some steps which will never happen unless I take times much greater than tau. You see, so when such systems are trapped, I cannot define the tau. That's what I'm trying to say. Or if you flip your question around and say, let me define, I'm going to look at things at fixed step delta, and instead of look at the distribution of times it takes to make such a step, a nice diffusing system will give you a mean time in which it takes a certain step delta. But the sub-diffusive systems, there will be some events that take very long times, so that the distribution of times will again have these fat tails, right? In other words, you cannot define a mean time because there are some very long time events with high probability because of trapping. Okay, so let's stop here. The main take-home message here is that so Einstein looked at this problem of Brownian motion and did this probability balance sort of idea, right, with some assumptions, and ultimately derived an advection diffusion equation. Okay, but we should keep these basic ideas in mind. We'll see how we make them more rigorous later. But we should also remember that not all fluctuating transport need be diffusion because of things like superdiffusion and subdiffusion, which are not covered by this derivation, right, because of our assumptions on phi and on tau. There are some more comments I want to make about this before moving to Langevin treatment. We'll do that in the next class. Thank you.